Hello, welcome to the video. Today I'll be exploring how Joint Embedding Predictive Architectures, so-called JEPA, are revolutionizing medical image domain adaptation. Imagine training an AI to detect tumors using pristine MRI scans at major well-funded hospital. But when we deploy that exact same model to a rural clinic using older GE scanners and with different settings, its accuracy catastrophically collapses. This is the core problem of domain shift. Traditional models and early self-supervised method often fail because they effectively memorize the specific noise, textures, and scanner artifacts of their home hospital rather than learning actual human biology. So, is there an AI that understands universally what a tumor looks like, regardless of the scan it was captured on? Yes, the answer is JEPA. Instead of forcing a model to recreate an image pixel by pixel, which wastes its time memorizing local noise, JEPA predicts the abstract latent meaning of the image. By shifting to this abstract representation space, JEPA acts as a natural noise filter. It inherently ignores scanner-specific acoustic artifacts and illumination changes, focusing purely on underlying semantic anatomical structure that remains invariant across any clinical domain. This allows us to create models capable of highly accurate cross-domain transfer using very little new data. This novel architecture's ability to address cross-domains is already reshaping specialized medical fields, leading to the development of foundation models. First, let's take acoustic ultrasound imaging. This imaging technique is notoriously noisy and heavily dependent on the specific machine used. US-JEPA stabilizes the learning process by using a frozen teacher model to provide clean targets, completely decoupling the learning process. Because it filters out modality-specific noise, even when we simulate extreme hardware degradation, mimicking a shift from a premium hospital scanner to a portable device, US-JEPA remains highly stable. Next, we see a similar cross-domain breakthroughs in neurology with Brain-JEPA. By using functional coordinates rather than rigid anatomical grids to track brain dynamics, it learns universal human physiology. Remarkably, a model trained only on Caucasian patients can accurately diagnose neurodegenerative conditions in Asian cohorts with zero retraining, overcoming a massive demographic domain gap. Finally, Echo-JEPA analyzes echocardiograms by predicting missing video frames in a clean latent space, learning the heart's true motion rather than distracting speckle. This focus on invariant anatomy allows it to seamlessly address the cross-edge domains, letting an AI trained entirely on adults accurately diagnosing pediatric patients right out of the box. But as we move from memorizing pixels to predicting abstract concepts, we encounter profound open questions regarding how this model adapts to new environments. First, can completely independent clinical domains naturally align their data without forcing them through heavy joint training pipelines? We don't know yet. It remains an unsolved mathematical challenge to achieve true zero-shot alignment without explicit guidance. Second, by aggressively filtering out local noise, do we risk accidentally deleting a rare tiny medical anomalies? The answer is a cautious yes. Because JEPA is trained to ignore fine unpredictable details, there's some risk it might make a microscopic early stage tumor for just another scanner artifact and ignore it completely. Third, does the specific physical structure of a medical image change how we train these models? Absolutely. JEPA is incredible for mapping large-scale global anatomy, but for highly localized microscopic patterns like those found in histopathology, we might actually need to safely hybridize JEPA with older traditional architectures to cross-domain effectively. And finally, to save computing power, methods like US-JEPA rely on frozen teacher models. But does this reliance prevent the AI from adapting to brand new medical hardware? It is a distinct possibility. If a learning model is permanently bounded by its static teacher biases, it might not be able to generalize to radically new scanners or artifact profiles that the teacher has never seen before. Making JEPA to work seamlessly across different medical domains isn't easy. We require solving some intricate architectural hurdles, specifically regarding optimization stability, biologically appropriate masking during training, and cross-domain alignment. The first is the issue of training stability. Because JEPA learns in an unconstrained mathematical space, optimizers often find a degenerative shortcut known as representation collapse. The network simply outputs the exact same meaningless vector for every input to artificially drive the loss to zero. To stop this, modern frameworks like SAL completely freeze the teacher model, providing the learning model with a stable unmoving target. We can also combat this using regularization, which applies explicit mathematical constraint to force the model's feature to remain diverse and meaningful. The second major challenge is how we mask the data during training, and you cannot black out random squares in 3D and 4D clinical imaging. In an fMRI, blood oxygen signals do not have neat structural boundaries, and random masking destroys the vital temporal flow. Brain-JEPA innovates here by abandoning simple grids and using brain gradient positioning. It maps the brain based on functional connectivity. It then forces the model to focus neural time series across long-range connections for unseen spatial regions rather than letting it rely on simple local patterns. Finally, we face the mathematical ambiguity of cross-model translation. Mapping a 3D point cloud directly to a 2D image embedding is what we call an ill-post optimization problem. Because multiple 2D views can legitimately represent the exact same 3D structure, the optimizer gets confused. Frameworks like Cross-JEPA solve this by explicitly feeding the model with geometric projection parameters. Although Cross-JEPA did not originate specifically within medical domain, its robust methodology can still be adopted for clinical tasks. By removing the mathematical guesswork of the camera angle, the model can focus entirely on translating the actual anatomy. Looking ahead, future developments will likely make these projection strategies adaptive and learnable to optimize this cross-model alignment. Ultimately, JEPA models can able to address the domain shift problem with a very simple rule. Learn the anatomy in the latent space while ignoring the artifacts. By stepping back from the noisy pixels and focusing universal semantics, we can finally build an AI that safely adapts to any clinical environment. Thank you.